Okay, I'm at the whiteboard, so I hope you can all hear me. Today's lesson is recognizing and using direct variation. Two variables, x and y, are two variables, x and y, vary directly if there is a non-zero number k such that the following is true. Y is equal to a constant of some sort times x. The number k is called the constant of variation. Two quantities that vary directly are said to have direct variation. So just to kind of give you an idea what this means is, let's say I had a value for y that was, let's say y was equal to 10 when x was equal to 2. And they're said to vary directly. So we have to find out what the constant of variation is for that. So what I would do is I would put in this y equals kx. I'd put in the 10. I'd put in my k for the constant of variation. And then I'd put in the 2 for the x up here. And now to find out what the constant of variation is, I just divide both sides by 2. And I get 5 is equal to my constant of variation. Okay? So when I write that, I would write it as this: y is equal to 5, which is my constant of variation, x. Now, if I were given any other number for y, like let's say I was given 20 for y, what would my x be? Well, it varies directly. So if y was 20, x would have to be 4. So that's how the constant of variation works. So let's take a look at our first example, graphs of direct variation models. So find the constant of variation in the slope of each direct variation model. So we know that the model is this: y equals kx. We know that, okay? So we can assume that the k is a 2 in this model. So we know that the constant of variation is the 2. And in this one over here in B, my constant, so let's just write that, k equals 2. And then my constant of variation in this one is k equals negative 1/2. But now it's asking us in the bottom here, in the solution, to find the slope of the line. To find the slope of the line when you're giving 2 points, like this 0, 0, and 1, 2, in this first one, 0, 0, and 1, 2, we can use the slope formula. And when we go down here, we have y2 minus y1, so we have 2 minus 0, and we'd write 2 minus 0, and we have 1 minus 0 for the k values, and we see that the slope is 2. We also see that our constant of variation is 2. The same thing over here, we can do the same thing. Here's our y and our y here, so I would go, we can start on this side, it's fine. Negative 1 minus 0, and then 2 minus 0 goes underneath, and we have a slope of negative 1/2. And look at our constant of variation. Our constant of variation is also negative 1/2. So we could conclude that the constant of variation is also the slope. Okay, let's talk a little bit about what the graphs look like for direct variation models. First of all, the graph of y equals kx is a line. It's always going to go through the origin. Then, in other words, the y-intercept is always going to be 0. The slope of the graph of y equals kx is always k. As we just determined in the last slide, k and the slope appear to be the same thing. So if we look at this graph, which has a negative slope, we know that the slope is negative, therefore k must be negative, so it's less than 0. And here's a positive slope, so here's an example where the constant of variation k is greater than 0. So this is writing a direct variation equation. So let's read the problem first. The variables x and y vary directly when x equals 5 and y equals 20. Write an equation that relates x and y. Then find the value of y when x equals 10. So we kind of did that on the first page, but let's do it again. We go y varies directly with x by some sort of constant. And we're trying to find out the constant. So if I substitute in a 20 for y, right, and I put in the 5 for the x, and then I divide both sides by 5, I find out that the constant of variation, k, is equal to 4. Okay? So now I can write the equation y equals, the constant of variation, remember, is 4. So I know that the equation of the line is y equals 4x. So now all they're asking me is find the value of y when x equals 10. Well, y is going to be equal to 4 times 10. So y is equal to 40. Okay, in example 3, we're going to write a direct variation model using a story problem. So it's a little bit tougher, but bear with me. In 1852, Henry Gifford built the first airship successfully used for transportation. It had a volume of 88,000 cubic feet and could support 5,650 pounds. The Graf Zeppelin II, built in 1937, had a volume of 7,063,000 cubic feet, making it one of the 2 largest airships ever built. The weight an airship can support varies directly with its volume. How much weight could the Graf Zeppelin II support? So our first task is, we know that the weight varies with the volume, with some constant. So we know that W, the weight, is equal to some constant times the volume. Okay? And with the first example, this 1852 example, they gave us both the volume and the weight. So we knew that 5,650 pounds is equal to some constant of variation times a volume of 88,000 cubic feet. So if I divide both sides by 88,000, right, I will get 5,650 divided by 88,000. Quick calculation here on my calculator. Comes out to 0.064. That's my ratio. So that's my constant of variation, is the k. Okay? Now that I have that, I can solve what the Graf Zeppelin weight could support. So we know that it's W equals, the constant of variation is 0.064 times the volume, right? So now all I need to know is the volume of the second ship, which was the largest in the world, the Graf Zeppelin II. The volume was right here, 7,063,000. So W equals 0.064 times 7,063,000 cubic feet. And when I multiply that, I find out that the weight is 452,032. And that weight is in pounds. The next goal is using a ratio to model direct variation. And the model y equals kx for direct variation can be written as follows, so that the constant is equivalent to the y over the x, y divided by x, the ratio of y to x. So the ratio form tells you that if x and y have a direct variation, then the ratio of y to x is the same for all values of x and y. Sometimes real-life data can be approximated by a direct variation model, even though the data may not fit the model exactly. So let's take a look at what that might look like. Using a ratio based on data to write a model, the tail and body lengths and feet of 8 alligators are shown below. The ages range from 2 years to over 50 years. Okay, so if we look, here are the 8 alligators, right? It's alligators. Their tail length and their body length. So their tail length looks like it's from here to here, and their body length is, you know, all the way to the nose, to the back, basically the back legs. And what they're saying is that the tail and body, if we can find some kind of ratio, some kind of constant between them, then we could also guess other body lengths and tail lengths for other alligators. So first of all, we'll write a model that relates the length of the tail to the body length, and that would be something like K is equal to the tail divided by the body length. Okay, so I'm going to just take the 1.41 and the 1.5 and I'm going to divide them, and that's what we've done already down here. So this is your tail and this is your body, and we're dividing them, and we're getting all these different ratios. So they're not exactly the same, but you could say that the tail to body length, the K is approximately 0.9. Okay, so with that information 0.9, estimate the body length of an alligator whose tail length is 4.5 feet. So I could go 0.9 equals, estimate the body length whose tail is 4.5. 4.5 divided by B. Okay, so I could multiply both sides times B, and I get 0.9B right here is equal to 4.5, and then I can divide by 0.9, and 4.5 divided by 0.9 is, B is approximately, B is about 5. So the body length would be about 5 in this example. So here's some guided practice. So the first question is, explain what it means for x and y to vary directly. Let me grab it. It means that there is a non-zero number, k, such that y is equal to kx. Okay? In a direct variation equation, how are the constant of variation and the slope related? Well, if y equals kx, the k is the slope. The slope is the constant of variation. Okay? State whether the two quantities have direct variation, and if they have direct variation, find the constant of variation. And what is the slope? Okay? Y equals x. So the variation here, there's actually would be a 1 in front of the x. So we'd say y equals 1x. We never write the 1 in front of the x, but the 1 is actually the constant of variation. So y varies to 2x with a slope of 1 and a constant variation of 1. So we could write 1 and 1. So the constant of variation is 1 and the slope is 1. How about this one? The constant of variation, the k, would be 4, and the x would, and the slope would also be 4. Okay? How about this one? Y varies at 1/2, so the constant of variation, the k, is 1/2. 1/2, k equals 1/2. I'll scribble this out. I don't need that. Why do I? So the constant of variation is 1/2, and the slope is 1/2. How about this one down here? Constant of variation is 2, and the slope is 2. This one, because there's a -4 here, we don't have it is not a direct variation problem. So not direct variation.